Harvey Mudd College.
I'll buy a beer for you. You lived in the States, though.
And then a Master of Science at Cornell. I think there's where you met Danilo.
Yes.
Yeah. And then a PhD there as well. And then he moved to Paris for a postdoc position. And then another one in Rome. And now he's a Simons Professor young investigator here, working on statistical physics, disordered systems, and yeah, the floor is yours, Jaron.
Thank you, Paul. Alright, so I hope by the end of this talk you understand something about this crazy title that I made. So, before I get started, I just want to acknowledge my collaborators who made a lot of this work, in fact. David Lamas is a student of Olga, a PhD student in Boston. He did most of the numerics you'll see in the later part of this talk. Olga and Adrian both were involved in this problem a long time before I joined. So they, let's say, the first quarter of the talk is mostly their work. And Kuhn helped with some of the asymptotic analysis you'll see. So this problem is the basic problem I'm going to talk a lot about. It's very simply stated. Before I motivate it or anything, I'm just going to state the problem. And the problem is this: you have a shape, and the shape has a fixed area, which is we're just going to make 1 for simplicity. And the idea is that somewhere on the shape you have a grasshopper. This is, let's say, a very colorful metaphor of my colleagues, but we have a grasshopper somewhere on the shape. And the grasshopper is going to jump a certain distance d. And that distance will always be a fixed length d, but it could be in any direction. So here's the circle of places the grasshopper could jump to if it started at this point on the shape. But we imagine the grasshopper has an equal probability, sorry, there you go, any direction it likes a fixed length. But the grasshopper has an equal probability of starting from any point in the shape. So it could start wherever you like inside the shape, and it has to jump a fixed length d in a random direction. And the problem is to find the shape which maximizes the probability that after the jump, the grasshopper is still inside the shape. Right? So some jumps take it outside the shape, some jumps have it stay in. You want to maximize the probability it stays in. So I already kind of spoiled by going one slide too far. But can anyone give a guess for a candidate shape that might be a good, let's say in some regimes of jump size, a good candidate for the maximum probability shape?
Circle.
So it's the circle or the disk is a good candidate. This problem is rotationally invariant. As physicists, we like to imagine that a rotationally invariant problem has some regime where a rotationally invariant solution is the correct solution.
Now, how do you define the space of shapes? Because you want to define probability on that space, which is a
on all let's say sets of R2 that measure 1. On all sets. They don't be connected, they don't be smooth, I don't care. All sets on R2 of measure 1. Yeah, the grasshopper is a point. So you start from any point in the shape and you make a fixed displacement of random direction to another point in the shape.
Is it shapes contained in a region?
No, but they have a fixed area. So.
Oh, it's fixed.
And the distance is fixed, so you wouldn't want part of the shape to be so far away. You're unlikely to land there. You want to maximize the probability you land again inside the shape.
So the answer is D independent?
Sorry?
The answer would be D independent?
Absolutely not.
Okay.
In fact, as I was going to say just now, so the circle may be a good candidate for small d, right? It makes sense. But certainly it can't always be a good answer, because eventually, if the jump size is larger than the diameter, certainly, it'll never end up inside the circle again. So it has to be some other shape for a very large d. Can anyone make another guess for a rotationally invariant shape that could be a good candidate for large jump size? No?
Excuse me, the shape of the area is not restricting the movement of the grasshopper.
The grasshopper starts at some random point uniformly drawn inside the shape and moves at a fixed distance at a random angle. It can go outside the shape, for instance. If it started here and jumped to D, it would always end up outside the shape. But we want to choose a shape that maximizes the probability it doesn't do that. We want the grasshopper to stay inside the shape. So we can't control it, we don't stop it from jumping out. We want the shape which maximizes that probability.
So there is that kind of exoteric shape of like flower of life. We can have a bunch of like not really concentric circles, but circles drawn like at the edges.
So let's slow way down. You can start with one concentric circle.
Okay.
So here's maybe a candidate for a larger jump size, an annulus, right? Because this is still rotationally symmetric. We could add maybe more stripes or something too. Who knows? We'll see when we look at solutions to this. But okay, in terms of rotationally invariant solutions, right? If I'm just pulling out the most naive ones, I would say the disk and the annulus maybe at larger jump size. But before I get to answers to what those solutions actually look like, I'm going to motivate the problem now. So why is it that we ever came to study this problem? It's a cute problem, but who cares? And the answer comes from certain kinds of Bell inequality experiments. So the traditional Bell inequality scenario is that you have two experimentalists, Alice and Bob, A and B, who receive spin 1/2 particles generated by some black box. And the question that they
Yeah, that is always the case.
The question that they look to answer is whether or not the particles they're receiving are inherently quantum in some way, they're entangled, there's spooky action in the distance, or if they're classical, in the sense that the properties they can measure of the particles were already fixed when the particles left the box and are local to the particles themselves. And so the traditional way to answer this question, the thing you learn in grade school, is that Alice and Bob both have two different measurements they can each make to the spin 1/2 particle. And so Alice, chooses between measurement 1 and measurement 2, Bob chooses between measurement 1 and measurement 2, and when you have two choices from each of the experimentalists, you have a certain inequality you get, which says that if the particles did have their information fixed locally, their classical in some sense, as they left the box, then this sum and difference of different correlators of the two measurements can only get to a certain value, which is 2 in this case. But in practice, people who want to make these kind of measurements, they typically are interested in the quantumness of their system for a reason, like they want a secure communication channel or something. And there, it's very important the efficiency of the channel. Like how quickly can you show this inequality doesn't hold and say that my thing is classical or quantum. And so you can imagine doing different kind of procedures. For instance, another kind of procedure is you let the experimentalist have n different measurements they make to the particles, n different axes on the block sphere that they can choose from to measure the spin against. And when you have n choices for each experimentalist, you have a different set of inequalities called the Brownstein-Caves inequality. Don't ask me about anything to do with this, I just copied it as you can see. But the point is it's different. You have different inequalities, you can play with the axes you choose and try to make it a more efficient procedure. So what my colleague Adrian was looking at basically a decade ago was a different kind of Bell inequality scenario, where instead of having a fixed number of possible measurements the experimentalists take, you say each experimentalist can do whatever measurement they want on the block sphere. A picks any axis they like, and B can also pick any axis, but under the restriction that the angle between the two axes of measurement is a fixed. So, you can imagine different schemes for making this happen, but whatever the scheme is, the measurements by A and B always happen at a fixed different angle.
Do you know why they wanted the check? There is an experimental reason for that. Do you know?
I don't know the details, sorry, I'm very sorry. You can look at in the next slide, the paper citation of Adrian. You can read like 2014. Because again, so the point is, why am I talking about this grasshopper problem? Well, so it's easy. This is maybe a simple exercise in quantum mechanics to say if I have a maximally entangled state, so what is the maximum quantum anti-correlation of such a scenario? You get some number, it's minus the cosine of theta, okay? But Bell inequalities are not based on a quantum calculation. Bell inequalities tell you what is the best possible classical anti-correlation you can make, right? Because you need to know, is this thing quantum or is it classical? Well, what's the most fake quantum I can make classically? And so the question is what is this? And the answer, which was given by my colleague Adrian and a student of his, I think, about 10 years ago, was that in this problem, the best local hidden variables theory, the best classical theory that gives you the strongest anti-correlations in this setting is one where the particles have their spin properties set by a coloring of the block sphere, which is antipodal, so opposite points need to be colored in opposite colors, and maximizes the probability that if you take a point in the coloring and you displace it by that angle, you will end up, again, the same color, right? So here's the grasshopper problem, but now not on the plane, on the sphere. And back then, they were able to make a quantum calculation, and they computed this, best local hidden variables anti-correlation for a variety of, let's say, stripy spheres. These are all rotationally invariant solutions. You have the hemisphere, 2 stripes, 3 stripes, 4 stripes. And they found, okay, well, you might imagine maybe the hemisphere is a good candidate, and for, 1 is the hemisphere, 2 is 2 stripes, 3 stripes, 4 stripes. This is the correlation you get between the experimentalists. For a lot of angles, it seems like the hemisphere it saturates certain bounds they are able to prove that are these gray lines. They're not tight bounds, they're just generic bounds. But it doesn't always saturate them. And actually, for very high angles, you see that some of the stripy scenarios have more extremal correlations than the hemisphere. And so they concluded in this paper, look, we can state the problem, but the answer of what is the probability that you have to beat to show that it's quantum, we don't really know actually. We don't know what sort of coloring you should make to do the best classical job. And so what they did is they said, look, this is a kind of a hard problem, but it's a very simple problem in some sense. Maybe we can solve it in a more controlled place, which is on the plane, right? This is the grasshopper problem. You do this in R2 instead of on the sphere. Yes, Papa?
What's the -1 case here?
Oh, -1 is literally, they just reflected 1 over the axis. So it's not some fancy coloring, they literally just wanted to compare, if you see, they wanted to compare how 2 and how 3 were doing up here, and so they just reflected this line. It's nothing sophisticated. So, alright, so the grasshopper problem. So I just described it to you in very qualitative terms, but you can make this quantitative. So you say, look, we want to go over the shape of subsets of R2, omega is a set, which maximize the probability that this thing happens, that when you start from a point in the shape and displace, that you stay in the shape, which is equivalent to taking a double integral over the volume of the area of the shape of some delta function containing the distance between the 2 points and the distance that the grasshopper is allowed to travel. And there would be a lot of normalizations if I hadn't picked the shape to be area 1, but the only normalization remaining is the perimeter of this circle. Right? So this gives you do this integral, you get the probability. And it's, of course, the whole thing is constrained by the fact that you have to be a fixed area. Is it trying? Would I remove the thing?
That is move the angles. If it's 1 is 5, if it's 2
It's not my computer, I think. Let me just check unplugging it a little bit. You try it. Oh. We just plugged it in. Alright, wait, can you get that for a moment? And then advantage again. It's USBC. USBC, this is HDMI. Let me take another adapter to check. Okay. Oh, it's back, Okay, I keep going for now. So, anyway. So this is the problem. But this is a very difficult problem. I mean, as physicists, we have certain approaches to problems like this, like extremal problems. This is extreme. Okay, extremal problem, off again, on again, off again. This is very exciting. Anyways, we have certain approaches to extremal problems, which are usually based on perturbations, things like this. But let's say optimization or extremizing of the space of shapes or of sets is very unusual. Let's say. And so, my colleagues, Adrian and Olga, I really like this slide change, so I'll time. They went about discretizing, discretizing the problem so they could put it in a computer, right? So they couldn't find any way to analytically approach this. So when they studied this problem, they looked at a version where you discretize space, your plane, and and you say, okay, sites are on or off. If they're on, they're in the shape. If they're off, they're not. You have a constraint on the number of sites that can belong to the shape, and you have some sort of regularization of the delta function. You know, they did this very carefully. I'm not going to go into the details of this. So the point is,
Well,
I need to allow it probably. No work.
We're back. Sorry, guys.
So now you can do this in a computer, and you can try to do various kinds of normal lattice optimization to find the S's, the ones and zeros, that give you a shape which maximizes this thing. But actually, this is itself a quite hard problem, because this is a long-range Hamiltonian, if you will, right? It's non-local. It connects different points at a distance d from each other in some circle. So computing this takes order n squared steps, and so that's slow. And also, as we'll see, the solution space is full of these metastable solutions that can capture you and trick you. You know, if you just try to take some random starting shape and quench it in some sense, try to find, go do gradient descent or something, you often find shapes which are stable but are not the maximizer of the probability. And so my colleagues Olga and Adrian did a very large amount of work.
The additional complexities in time, right? Memory sounds.
Yeah, memory is very easy. It's time.
Indeed. Yeah. Okay.
So they actually attacked this problem by using a common algorithm in statistical physics called simulated annealing, where you start simulating this problem, this lattice model, like this is a mountain energy at a high temperature, and then you very, very slowly lower the temperature, so that at each stage the system has a chance to try to explore different, let's say, metastable basins of the free energy, and always stay in the one that will in the end be the ground state. So
the computational problem is easier if d is smaller,
yeah, if d is smaller, it's easier, of course.
and then you recover the superposition.
Well, we'll see in just a minute, because we're having a little break from the slides to look at some videos that they made in the supplementary material of their old paper in 2017 of this simulated annealing. We're going to see exactly what kind of shapes we find. So with this, I'm going to start a couple videos. So this is going to be, I forgot my paper. So the important thing is that, keep in mind when I show you these videos, because the area is 1, this is a stupid normalization in some sense, the radius of the circle is a weird number, right? The radius of the circle is 1 over root pi, which is about 0.56, I think. So when you see numbers about what d is, you should keep in mind d relative to the radius of the disk, right? That's the important length scale. So here's for a very...
But d is also fixed, right?
D is a fixed d, and then you find the shape that's best, right? So each d has its own best shape. So what's 4? There you go. So here we are. This is the starting, the initial condition, let's say, of a simulation, and we start at some high temperature and we slowly cool. So we're nearby a circle. It looks very nice. And now you can kind of maybe see some kind of instability forming here around the edge, and we cool and things move less, and we find it's not a circle, the best shape here. It's some kind of weird,
So you have an ON symmetry.
weird kind of cogwheel. Well, it's a discrete symmetry, yeah.
Discrete symmetry.
It's a discrete symmetry, yeah. So this is for us, this is like about half of the radius. So you can sense some small.
Do you understand I mean, from first principle, the degree of this discrete
I'm going to get into this. This is part of the work I contributed to this problem.
Okay.
But first, I'm just helping you watch the next video. So here they're starting from a very high temperature. This is larger. This is comparable to the radius in some sense, but below. And here they lower the temperature, and we get some other. This is also, I think, going to end up being a shape with a discrete 6-fold symmetry, or 7-fold? 7-fold symmetry in this case. Very nice.
It looks like stuff from a favor.
Then we move up. So this is a little bit above. You see, there's a kind of a metastable thing. it started almost going to a 5-fold symmetric, but then it found this thing, which has no symmetries, I believe. This is slightly bigger than the radius. So yeah, this shape really, they hammered this one for a long time. They increased the lattice size. They were like, this must be wrong. This is something like this is the best shape you get for deep.
Sorry, do you have any way to understand if you ended up in an horrible landscape and then you try? Do you have a way to understand if you are metastable or stable or no?
You can do simulated annealing slower and slower.
Okay.
Which is one thing you can try. You can also try doing something like parallel tempering, which is like simulated annealing but lets you exchange up and down in temperature. And this you're more guaranteed to follow.
So let's say you are reasonably
Yeah.
convinced that this is.
They did a lot of work. They did a lot of work in this paper that convinced them that these are the good shapes. All
What
right.
is the meaning of those islands?
Sorry.
What is the meaning of those islands that you have in this last?
I told you there's no restriction on the shape except that it maximizes probability. It doesn't have to be a compact shape.
No restriction of the shape of the surface.
You know, it's just a subset of R2. Any subset of R2. It could be fractal for all we know, but if it's not, it happens to have, let's see, it's things like this. But this is a very small change. D equals 6.2.
This is quite symmetric.
This one, we got some symmetry back, right? We now have some near symmetries returning. Now let's see, that was 6.2. Our next one is 7.8. Okay, we're jumping forward. Oh wait, that was the wrong one. 7.8.
And does it depend on the size of the cells, the grid cells?
So they did a lot of work to see that the shape they find doesn't. So they, doubled found the shape that was good, and then doubled, tripled the fineness of the cell, and made sure that what they found was asymptotic. So this is a nice one, the fan here, and then more again symmetry.
There is a hole in the middle.
Yeah.
It's true, it's true. Oh. And then finally, there's one more video at 0.9, almost twice the radius. You see this one? Watch, this one is great. You see, oh wait, this is not it, there's one more after this. Here there's a metastable state where a fifth stripe almost formed, right? There's a fifth stripe and it dissolved because they tempered it slowly enough. And you can see that the ground state is these 4 stripes. And actually for all D greater than this, it seems like 4 stripes like this, something like about this is about the good answer. Alright, so our video time is over, our movie time is over, we can go back to the work here. Okay, so as a quick overview, so this is from their paper. At small d, you never find the disk as the answer. You find these, they call them cog wheels, or like they're gears. A cog is the one part of a gear that does this. These are cogs. So a cog wheel is a wheel of cogs, or a gear. So these are, you find these of different symmetry for small d. If d, so this is up to the radius of the disk, right? And then for slightly bigger than
the circle come out as a sort of d equal to 0 limit, maybe, because they are becoming more and more.
Yeah, we can see this maybe in the next part of the talk when we get to my work. So here around a little bit bigger than the radius, you see this is almost a symmetric shape, but actually it's not. It has a 3-fold symmetry because every other one of these cogs is a slightly different shape. And then we have the next regime where things get kind of crazy very rapidly. So these shapes are spaced apart by like 0.1 in the distance jump. You can see they're quite different in terms of what they look like. And then there's a regime of these sort of 3-fold symmetric fans with little symmetric islands and eventually a hole in the middle for another regime of D. And then finally at large D, you have 4 stripes, and this 5 stripe, which is sort of a metastable state. It's a higher probability than the 4 stripes. And so this is sort of the phase diagram they found in this paper in 2017, using this numerics, which is, okay, you never have a disk, you have this menagerie of crazy shapes. So this is, up to this point in the talk, I was not part of this work. I entered this work because I watched a talk like this in Paris at Boca, who got to the end and said, this is crazy, I mean, look at all these funny shapes. And I said, I have an idea. Maybe there's a way to treat this analytically based on some very deep similarities between this problem and some problems in ferrofluids. So what is that deep similarity? So the form of the probability functional, right, in this problem, is a double integral over the area of the shape of some function, this delta function, okay, it doesn't matter, it's a function. It depends on the distance between, only on the norm, right, of the difference between the 2 points that you're integrating. And I actually worked on a problem very similar when I was a bachelor's student, in which you look at ground states, equilibrium ground states of ferrofluids in 2 dimensions. And there you have an energy functional, which has one piece which is like the perimeter, it's like a line tension, it's not important. But you have another piece which looks like the dipole-dipole interaction inside the fluid, which looks like a double integral over the area of the fluid of this dipole interaction, which depends only on the norm of the distance between the 2 points. So structurally, these 2 integrals, these 2 functionals, the shape are very similar. And so this plot here is actually from a paper of mine. These 2 top parts are from experiments. These are so-called Keeley-Shaw cells, where you crush a ferrofluid between 2 metal plates, or 2 glass plates, and you put a field on it, and it makes nice shapes. These are Langmuir monolayers, so they're like polymers, like a cell wall, where the polymers, where the little cell wall pieces have a dipole moment, so they also make funny shapes like this. And this is actually from our simulations of these things. We developed a way to, you can see this is a very fine scale simulation that reproduces what these things look like. And the question, I think, the thing I can tell Olga is, look, I was able to make these fine scale simulations on a much finer scale than you were with equally long range energy. And how was I able to do that? Well, the answer is, there's a nice way to treat this kind of integral, to convert it from an area integral, which is hard to do analytically, it's hard to treat analytically, and hard to treat numerically, to a line integral. And line integral actually goes much simpler. So what does this look like? So here's the general formula, right? You have some integral, which is a double area integral, over a function that only depends on the norm of the 2 points you're integrating. So you imagine that you find some second function, which is related to the first function, in that it is the Laplacian of the second function is the first function, right? This is just an ODE in spherical coordinates, you can solve it, it's okay. If you find such a function phi, you can use the generalized Stokes theorem twice, and the symmetry that you get from this norm to transfer the double volume integral into a double surface integral over the perimeter of the shape.
So my memories of calculus are
What
are the conditions for the existence of such that you can write f in terms of the Laplacian?
I don't know in general, but RS
is quite easy to check. Most of the functions can be represented in this way.
You can, okay, I would say take your favorite f and try. I mean, the point is, there's an explicit formula, which I don't have on the slide, but it involves, you write down the Laplacian. This is only a radial dependence, so you only have the radial parts of the Laplacian that come in, and you can invert it by making certain kinds of integrals of this with 1 over r's and r's involved. And presumably, if those integrals are convergent, then you're good. If they're not convergent, then you're not good. In this case, they're convergent, so you get answers. So for a ferrofluid problem, you convert your double, yes?
Doesn't that constrain the kinds of shapes you can have for continuity reasons, for example, or like these islands that appear, that kind of stuff?
Yes, I would say it doesn't. This is general in terms of the connectedness of the shape, because your perimeter just has to involve different pieces that have to be integrated against each other in all possible combinations. It's a mess, if it's possible. But it's true that it does depend on the smoothness, I think. So if the shape isn't smooth, if you have certain kinds of singularities or cusps, then you have problems. But fortunately, we don't have that happen. And in fact, I'm only going to be using this analytics in the regime where we have one compact region, so it's not a problem.
Maybe I'm anticipating, but is there any reason why the best area is always smooth? Let's say,
I don't know the answer to this. It's a good question. I have no. It won't come.
Because it could come out also something very, as you said, fractals.
Yeah. Why not have like what's the set of measure 0 that covers the whole line, you know. You can do this. But the thing is, that kind of set, yeah, the Cantor set. But that kind of set, you have 0 probability of landing in.
Yeah, but it's not fully connected. I mean, the simulation gave you things that were not so. I don't know what you mean by smooth. No, because it's not continuous. I mean,
Now, what smooth means that the boundary can be described by a continuous function that is differentiable.
But in the simulations, you have finite size cells.
It's
so
true,
I
it's
guess
true.
You can see them. Anyway, but this is analytic.
Anyway, so this is the nice mapping you can do. And you see, okay, you can solve this problem for the delta function, and you get something which is like a log and a heaviside function. But the point is, if we look now at what this does, or if we look at what this does to a probability, this is a much simpler formula. This you can give to an undergraduate student, right? This is a double line integral. If, again, so this is, imagine that I've parameterized the boundary of the shape by some r of theta. This is now, I've assumed that it's a single piece. But you could also add multiple pieces and have, let's say, a sum over all the pairs. Excuse me. Well, then you just have a double line integral over this phi, this kind of line potential, also with the dot product of the tangents of the 2 points of the 2 integrals. But this is now quite simple in some sense. And we can start to play with it. So for instance, the thing that I'm going to talk about the computation of is we're going to analyze the stability of the disk to small perturbations of a certain symmetry. Yes.
I think that in this direction, the input data go from 0 to B, and here, like this, 0 to 2B. But I see you putting 0 to 2B, 0 to 2B.
Sorry?
The two direction of data.
Yeah. They both go there. R is a periodic function, so I can put whatever boundaries I like.
I think it's the same angular coordinates, not like 2 angular coordinates.
So, if I want to analyze the stability of the disk to small perturbations, I can look at a boundary which is parameterized by an angle, is constant with a small sinusoidal perturbation, and I can ask whether the probability due to this is slightly raised for the small perturbation or slightly lower. If it turned out to do this, you have to look at second order in the expansion in epsilon. But, okay, so this coefficient, delta p, which is the coefficient to the second order in epsilon of the probability, will tell you that it's positive. It means the probability went up when you added the perturbation. That means that the disk is unstable. It's the opposite of normal physics here. Whereas if it's negative, it means that it was less probable that the disk should be at least locally stable against these perturbations. So this problem you can do. I mean, this is not a nice integral. You can look at the appendix of our paper if you want to know more about it, but it can be done, and the answer is very simple. You just get this nice equation in terms of this angle phi naught, which is literally just the angle that corresponds with the distance d between 2 points on the disk. So if you have 2 points on the perimeter of distance d, then this is the angle that separates them. So this is this phi naught. And so this function I plotted here for a variety of symmetry breaking orders n, in case it's kind of a mess. I'll guide you through this for a second. So first we see, for sufficient, if you truncate at some n, so say this is n to 11, so it's a certain order of symmetry breaking. For sufficiently small d, for small jump sizes, you are always negative, which means the shape is stable. So you're not unstable at small jump sizes to large wavelength perturbations.
So that means that large n are good, that they improve the stability of the solution, right?
Yeah, so as you see though, so the other thing is that as you increase d at fixed n, eventually each of these becomes positive. And the place at which it becomes positive decreases, like the inverse of n, as you increase n. So, for a given d, if I fix myself at a certain d, I can make n larger and larger, and eventually there will be a perturbation at some high n that destabilizes me. So the disk is always unstable to these high n perturbations for large enough n. It's these points here show you for each of these the first place where that order becomes unstable. So for this problem with stability analysis, we can't hope to do anything very precisely quantitative, right? Because all of these transitions I showed you are very clearly first order, right? There's no continuous deformation of this thing between the different cogwheels or from the cogwheels to the asymmetric shapes. But we can, there actually is a lot of quantitative understanding that we can get out that's a little, let's say, fuzzier. So for instance, here you can see, we can look at, for a given D, what is the most unstable modes at that D? So like, here at 0.5, the most unstable mode might even be maybe 11 or something, Or for 0.6, the most unstable mode might be 9, right? The most unstable modes, the maybe first and second most unstable at each D. And when we do this, those first and second most unstable modes are given by these colorful blocks here as a function of D for just fixed D. And the actual symmetry of the shapes which are found in the numerics are in the black. And you can see that the first couple most unstable modes do a very good job of describing which symmetries appear in the actual shapes. It doesn't last very long. There's like a certain amount of time, it takes like 20 minutes, right?
Yeah. So stability means it goes back to the spherical.
The stability means that the disk is a better probability maximizer than the shape that is.
Right. So the perturbed then comes back to the disk.
If you were doing the Monte Carlo or something, yeah.
And then if you have a stability, it means the perturbation grows.
Yeah, it means that by making the perturbation, you increase the probability, and that at least a second order in epsilon, the larger it is, the better probability you have. Right? So second order, it says make the size of the perturbation infinite. We love it, but of course, eventually higher order considerations come into play and stop you at some finite perturbation size. Right? So I mean, it's a very common thing in kind of nonlinear physics that you do a linear or quadratic stability analysis. You find certain instabilities, and those instabilities show up in your pattern formation. But your pattern formation is usually super far from the linear regime, right? The cogwheels I showed you were not small perturbations. But nevertheless, a very large portion of the time, the most unstable mode will be the one that actually appears in the patterns. So this is what we're seeing here, for instance. So even though it's not well describing in some sense the very big oscillations, because we did an expansion, it's still saying, okay, the most unstable one is pretty close. It's a pretty close guess. So we're still off. Anyway, the other thing that you can do, but you have to believe me until you can see the slide, is that, the curves, the continuous curves here, are just the location, there were curves that kind of follow the points. They're the location of the first peak of that function as you change n continuously. Right? So all those functions they went down, they passed through 0, and they had a first peak. So that first peak, that blue curve was the location of the first peak. It basically was exactly the thing we'd like to see to predict where the instability will be as a function of n. The other thing we can do, which you don't see right now, but which I have to believe, is that actually, even though these shapes are very far from the perturbative regime, the probability, the probability that they represent, the probability that is given by a certain cogwheel, is very well described by taking our second order perturbation coefficient and multiplying it by some estimate of epsilon that you get by trying to fit a sinusoid to the thing. And in fact, my colleagues in their old paper had this data they never used at the time, where they took cogwheels of different symmetry breaking orders, and they forced them to be, say, okay, we're at some D, where there's a certain ground state, a certain maximum probability state, and we're going to force the shape to have a certain symmetry that it doesn't want to have. That's a suboptimal symmetry. And we see what the best probability we get from the suboptimal symmetry is. So this is like saying you're looking at fixing D to some value, and you're looking at the probability that you get from the shape as a function of n, the number of cogs in the wheel. And if you take their data and you estimate epsilon, this amount of the size of the sinusoidal perturbation, and you look at the prediction of the probability, it's very well accounted for by just this second order term. I mean, you get within error bars, mostly, the actual quantitative value of probability in these metastable states. So again,
Is this right to say
yes, again.
you can predict number of cogs or a given B
Yes, exactly.
by looking at small perturbations?
By looking at small perturbations.
And then the perturbation that's most unstable is the one that gives you number of cogs.
It's always the first or second most unstable.
And what happens in that situation when you don't have cogs?
So when you don't have cogs, you don't have a perturbative regime. I mean, I don't have any analytic results for this regime in the higher D section where everything becomes crazy. But I do have more analytic results about other dimensions, which we'll get to in a second if we have a screen with you. But yeah, so I mean, what we can hope for from these integrals, you can implement a better numerics. So there's hope, which we haven't done, of making a numerics, which would be a little challenging because you have these multiple pieces of your domains, where you parameterize, you discretize your problem as the boundary instead of discretizing the bulk. And this is much more cheap. Oh, here's the nice thing. It's much more cheap to do this compared to discretizing the bulk, and you can make a much finer approximation with the computer. So one can hope to do this, but in terms of other applications of this integral form, once you're far from simple shapes, you can't evaluate the integral analytically.
So essentially, so just to be sure that I understood this one, you can describe the larger, because, I mean, here as far as I understand, it was important to start with the big guess that was the circle and then do the deformation around. Yeah. Instead, you cannot do the large D because you don't have an indicative guess to start with, or...
I mean, you can make whatever guess you like. The actual problem is that the integrals are not analytically tractable anymore. I mean, you could do a numeric integral or something, but the point is, so one thing you can do is if you know your shape as a pieces, you can even parameterize the boundary by Fourier modes, and instead your discretization would not be of the boundary, it would be of the number of modes, and then you could use n integrating Mathematica and find ones that seem to be optimizers. This is all fine, but once you move from very simple geometries, I can't give you a formula anymore.
Now, in the simulations, they also start with like a circle and then start to explore the space.
You saw some of the simulations. The first one started with a circle. The other one started from very high temperature. So it was like a high temperature Ising model. You saw in the videos, right? It was almost completely random.
Okay, but if you started with a circle, maybe you could have a transient where your analysis could be applied.
Yeah. So
if it breaks up into several domains, because
sure.
and maybe there is something there. I
There's
mean,
a
you start
zoo
with the circle, and then you see the instability develop, and eventually it breaks up into different domains, and maybe that first instability has something that is related to the final outcome.
Almost certainly true, but
no, I don't know, but maybe you can use that for the transient, and the transient gives you something. Because in the helixal cell, the experiments you also inject the fluid in the middle, you start from the circle that
in the ferrofluids. This is not the ferrofluids. Even though the pattern formation is sort of reminiscent.
So, but you said it was similar.
The form of the
viscous fingering, and you have the Laplacian equation, Poisson equation.
Yeah, but the form of the energy function is quite different.
Okay.
Okay, so this is
so you're saying that you're saying that the weakly nonlinear analysis is both necessary and sufficient to describe.
Sorry?
The weakly nonlinear analysis.
Yeah.
So when you go to second order, is necessary to capture
yeah,
results, but it's also sufficient.
Yeah. Yes. I mean, so linear is 0 because it's a symmetric problem, right? The cosine and minus the cosine of the same perturbation is a symmetry of the disk, right? So the only thing you can do is go to higher order than linear. So it's the first highest order from linear, and it does a very good job. So this is the thing I was saying. This is you fix D to a certain value, and then you force the shapes in the computer to have a certain number of a certain symmetry, even though they don't want to. It changes the probability away from the maximum. And you compare this normalized by the estimate of the size of the optimal perturbation to what you predict, which is a pure cosine in our formula, and it does a pretty good job. All right. So, what's next? Oh yeah, so this is the summary here. This is part of the talk. So, okay, we have this very nice phase diagram with all kinds of crazy shapes. We understand now very well the instabilities and the resulting symmetry formation in the small d part of the phase diagram. But again, with perturbative methods, we don't really hope to treat this. So with the integral form, it's possible we get a much better numeric approximation of this symmetry. But next, I'm going to move on to another problem, which is to do this in a higher dimension. So imagine using 3D, exact same problem. You have, okay, this is an arbitrary d, but imagine it's 3D, and there's the number as the dimension, big N. So it's the same problem. You have a double integral over the shape of this delta function. Now you just have a different normalization, which is the area of that perimeter. And you have a different function when you get from your Laplace transformation. It's not that interesting. And there's a constraint with the volume response. It's the same problem in 3D. So who wants to guess what, for small d, the optimal shape is in 3D?
COVID shape.
Sorry?
A COVID shape.
COVID shape. Come on, make an easier guess. You look foolish. No one wants to do it? Come on.
Sphere.
The sphere. Look at that. Pedro does it. For small d, indeed, the perfectly symmetric sphere is the solution in 3 dimensions. And then, exactly more or less, the diameter, the radius of the sphere, the next best solution becomes the 3D approximation of an annulus, also perfectly rotationally symmetric, with a nice hole in it to account for the fact that your jump side has gone too big.
Do you have simulations for that?
These are simulations done by David Lamas. This is very difficult simulations to do, let's say, because I mean the problem is much harder in 3D. You look at the paper. We had a lot of referee arguing about these simulations and whether or not we converge and things like this. So this eventually transitions continuously into a kind of cubey thing, which eventually becomes bulbous, and then of course gets into some more interesting.
Sorry, I completely missed why in 3D the spherical shape.
I'm going to explain it. I'm showing you the numerics. So this is the 3D phase diagrams. It's a little different than the 2D, and then we actually have the naive solution in some large regime. So next, actually, we have another break. I don't have a simulated annealing of these, but I do have some very nice animations of the 3D shapes spinning around that were made by David, which are very, I mean, you have to watch them. They're so nice. So only of the non-trivial ones, let's say. I don't have the sphere spinning around. You don't have to believe me that it's a sphere.
So the different colors means what? It's like you have a border.
So this is
it's sort of transparent.
It's a kind of it's like glass. So the fact that you see this this lighter region is showing that there's a hole. There's a hole inside this, right? It's like the more you're looking through, the darker it gets. So this is the shape you get out of the sphere. It's sort of a dice, right? And when you play a game, like a die. It's very nice, I guess. So then we have, there's only 4 of this one, so it's not so long. We have the next shape you get after.
It's not a sphere.
Oh no, so it was a sphere. The first 2 were sphere and empty sphere. Right? This is the first non-trivial shapes.
It's not a sphere with a hole in it. It's a dice with a.
Well, first, it's a sphere. Then it's a sphere with a hole that's perfectly symmetric, up to numerical accuracy. Then it's the dice.
Then you get discrete symmetries again.
Then you get discrete symmetries. So here's the next phase, let's say, which is a little more interesting. These were a lot of work. These are so much fun, these ones. All the students of Mola David did this. Finally, this guy, slow these gifts down. Look at that. These are much more symmetric. There's no I find the one shape of the 2D, which was had no symmetries. I find it looks a lot like the Wu-Tang Clan symbol. But there's no such complete lack of symmetry.
For this shape, it is the radius of the jump is larger than the sphere would be.
Yes. Because remember I think it's not actually. This is oh man, I have to remember so this shape here is the D is 1.3, and in 3D, the radius is something like 0.62, I think, if I remember correctly. So this is a little more than bigger than, it's a little bigger than the diameter. A little bigger than the diameter. And then finally, the last shape, which is this sort of double arc, and it seems to be the shape that lasts with a very large D. Anyway, oh, it's nice. The problem, has some similarity to the former problem, but also the big question, which I'm going to answer for you. I'm going to pretend it's the biggest question because it's the one I can answer. Is why does 2D have instability and 3D have no instability for small perturbations, for small jump sets, let's say? And I don't have, right now, an integral treatment of the sphere, or this, this hollow sphere, which actually this would be very nice if anyone's very interested in a lot of integrals. This is a continuous phase transition, so one might hope to do a very precise quantitative prediction of this transition point. But it's a very difficult problem compared to the disk because you have a lot of integrals. You have surface integrals, double surface integrals you can do. It's a bit of, and this is a quadruple surface integral, right? So you have two surfaces. So it's a bit of a mess. So I haven't done this. But the idea that I wanted to share is to study instead, imagine, because we're thinking about the instability of very small d to very small wavelength perturbations, which are much smaller than the curvature of these shapes. And so the idea is to study the stability of, let's say, if you zoom very, very close to a shape, it looks like a sort of infinite half plane. For 2D, it's just like a plane with or boundary. And for 3D, it's like a C, the top of the C, right? And the idea is if you go very close to the shape, you have wavelength much smaller than the curvature, is such a thing unstable or stable to small perturbation? So that's the name of the game. So you imagine your shape is some sort of, now it's not area 1, it's area infinity, but it's an infinity we know, right? It's half of the real numbers, right? It's all, for 3D, it's all numbers with the z that's negative, let's say. That's the surface, that's our shape, and the surface of the shape is just z equals 0 for 3D, right? X and y is all numbers, z is 0, that's the surface of the shape. So there's just how you define, right? You have, so the boundary of the shape is just given by, epsilon is 0, it's just given by all x and y with z is 0. And then we perturb the boundary. We add some nice waves, just like the ocean, right? And we ask if the relative probability, which neither of these are now normalized, but physicists should be very accustomed to this kind of thing. The relative change in probability due to adding these perturbations increases or decreases. If it increases, great, it's unstable because we want to maximize probability. If it decreases, then it's stable because we've made it less likely that the grasshopper stays inside the domain, right? It's okay, we can take our formula, and in general, for general perturbations H, we can write some expansion in epsilon, and again, the quadratic term is important. And you can see the quadratic term has some sort of integral formula, which actually is a lot nicer than even the disk, because these are integrals that just go over the plane. There's no funny business you can do with points that see each other periodically. And once again, with some normalization due to the fact this is not a bounded structure, we can define a coefficient, delta p, which if delta p is positive, we have increased probability, and therefore we have instability to that kind of perturbation. And if it's negative, then we don't have instability. So this is a calculation that we can do. Here's the answer. It's something with Bessel functions and gamma functions. But in 2D and 3D, it has a specific form in terms of cosine and the normal ordinary zero belt Bessel function. We can see, okay, in all dimensions, these are plotted for a number of dimensions from 2 to 11, just to be very showy. Really, we care about 2D and 3D right now. So in all dimensions greater than 2, so 2 is special. Every other dimension you see, for whatever jump size you like, this is normalized by the wavelength of the perturbation. There's kind of scalar variance here, if you like, because it goes size to the shape. Whatever jump size you like, or whatever perturbation wave number you like, you're always stable, right? The change probability is always negative to add this small wavelength perturbation. Except, okay, this is 0 at 0. Why? Because that's translating this shape. You're not allowed to do that. That would not conserve probability. But for 2D, you have a difference. 2D, this cosine minus 1 for wave numbers exactly commensurate with the jump size perfectly touches 0. So it's not unstable, this half plane. It's marginally stable, right? It's 0. You don't change the probability at all by adding the small perturbation to the half plane. And in fact, this seems to be true at higher order too, for 2D, which is an interesting thing. I won't get into that. So 2D is, in this sense, in this planar approximation, marginally stable with small perturbations. Oh yeah, and you can see, for instance, this is the 2D curve and dashed, I say any infinity, compared with the finite n curves from the disk, scaled in the correct way. And you can see that yes, indeed, as n gets very large, so we're having perturbations whose wavelength is very small compared to the curvature of the disk, we asymptotically approach this cosine. But, importantly, we do it from above, right? So, the infinite version is marginally stable, but at every finite n, we're slightly positive at the peak, which is why the disk is unstable. This kind of tells us it's almost an accident that the disk is unstable. You know, it's not like 2D things will be unstable. It says, in this geometry, plane, the disk is unstable because, I don't know, some accident with the disk. In fact, you can see this more clearly. This is a shape I dreamt up when we were still trying to figure out what to calculate. So, but we found the paper. I dreamt it. It's in my Mathematica notebook. It's the semi-infinite cylinder. So it's no longer a whole C. You wrap around. It has a finite perimeter, and you ask, is this semi-infinite cylinder unstable or stable to perturbations? And the answer is, it is stable to small perturbations. Right? This is all these peaks are negative. When you look at for a large wave number, so this is 64, so 64 times around the perimeter of oscillation, you see that compared to the half plane, right, which is always just exactly touching 0 with marginal stability, the disk approaches slightly from above, unstable. This cylinder approaches slightly from below, stable. So it's not inevitable that your 2D shape is in fact unstable with small perturbations. So with that, I am mostly done. So I described how certain integral transformations stolen from studying ferrofluids can help analyze these strange systems of things which are eventually hoped to inform us on novel Bell inequalities. The instabilities of small jump size we now mostly understand, and we understand also very well the difference between the 3- and 2-dimensional cases. And finally, okay, I can't comment on this stuff, but my colleagues who are more quantum than me assure me that the 3D version of this may find experimental application in certain kinds of quantum simulation experiments. But before I end and take your questions, you must, like Dario is probably very curious, right? This is the question. I told you 2D is marginal in principle, but the exact shape changes the stability. So the disk is unstable, the cylinder thing is stable, but the original question, which is the block sphere, is the hemisphere, which is kind of like the disk of the block sphere, is it stable or unstable with small perturbations? Actually, I think Olga and Adrian got their first paper out, and they said, look, we answered it, right? We found out that the disk is unstable, so this should be unstable. But this paper raises a question, which is actually, we don't know if this should be stable or not, because it's another 2D shape. It should, it's marginal in principle. But actually, there's been some numeric work on the archive of a bachelor's student, I think, of Adrian at Cambridge, who had something, Cambridge, they have some sort of keystone project, who simulated some preliminary simulations of this grasshopper problem on the block sphere. And I can show you the pictures of this preliminary work, which we haven't done any stability analysis or anything like this. All we have are these nice pictures of this bachelor student. You can see, so this is a little confusing. This goes from small angle down in this corner, and the angle becomes bigger as you go up, opposite how you might think. As you can see, also you get interesting forms of symmetry breaking. Now, I wouldn't trust these are necessarily the maximizers. I don't think they worked so hard on the numerics as the original paper, so these might not be quite the maximizers, but you can see clearly there are strong instabilities towards pattern formation on the log sphere, it's a quantum problem. As you move the angle higher, things get really crazy. These look like ferrofluids, right? This is like pattern formation of ferrofluids. This is, I love the one that gets very close to pi over 2. Pi over 2 just seems completely incoherent. This might be a Cantor set at pi over 2, I don't know. It's quite, but the thing is, this is all such preliminary data from this bachelor student, I couldn't say. And then for very large angles, this is larger than pi over 2, okay, we again have interesting kinds of, lumpy stripes, not even stripes, lumpy stripes, all kinds of fun stuff. So in the end, we have, let's say, this is the original question. It's not fully answered. Let's say it would not be answered very accurately here. I would give these very long error bars probably. But clearly, the simple naive answer of the hemisphere is not the answer. So the same kind of instability that drives the disk away from marginality must also be driving this block sphere hemisphere problem away from marginality.
This is the undergrad student paper.
This is the student, yeah. This is it's on the archive. It's like a Cambridge Keystone project.
It's clear that this is student young, otherwise we would have put some quantum in the title of the citation. It's clear that.
Why is there one having to study of this?
We haven't done it yet.
It's just not that we haven't done it.
I think so the integral transformation I showed you becomes a lot trickier because it's not Stokes' theorem on Rn, it's Stokes' theorem on Sn. And it's, I mean, we haven't looked at it yet, but I think you have to be a little more careful about how you do the transition from the bulk integral to the line integral.
But you've done it.
Yeah, 2 points. It's a very nice problem, you know. But I mean, look, the answer is not so deep. I did all this word question, you want to stop me to tell you it wasn't so deep. I mean, the wavelength is right commensurate with the jump size. That's what we find, more or less. All right, that's the end of the talk. There's no more slides. So I'm happy to take any questions. Anyone?
Questions?
We can go back to the other scenario.
Could this, could this calculation or here to explain things like surface growth, crystal growth, KPZ equation?
I mean, KPZ solutions are fractal, right?
Sorry?
KPZ equation solutions are fractal, right?
I don't know so much about it, but a long time ago I read how they were doing these calculations, and they did a lot in the way that you calculate the probabilities of extending the surface. And in that, people like, I think, Shapiro and Parisi and that sort of thing were using theory.
Yeah, I mean, I know there's a lot of work on KPZ surfaces, but I think because they're fractal typically, they're not smooth, this kind of integral approach doesn't apply. You need a smooth boundary in order to describe it with an integral differential approach, let's say. But I don't know, I really don't know very much about it.
Yeah, you look very simple.
Teacher, very cool. The videos were quite nice.
I didn't make any other videos completely different from me. I only, for the 3D videos, I gave some feedback. I was like, oh, what do you do this? But that was my role in that part of the
As you get more senior, you'll get more credit.
Oh, I did a lot of integrals. I did a lot of integrals, but I did not make any simulations.
But I have a question about the 2D case.
Yeah.
In the 3D, you go all the way to d equals 0. And in the 2D case, you stop it to d equals 0.2.
Yeah.
would you expect as D becomes asymptotically close to 0, the circle to come back?
No, you just keep getting cogwheels larger and larger frequency.
Okay.
So, I mean, I don't know. I'm not familiar with that part of the work. Well, let's look actually. So, if we scroll, where's my mouse? Here's the kind of answer to that question, right? So what's happening? We get more cogs as we go smaller d, and the amplitude becomes smaller. So in some sense, yes. I mean, there is a sort of approach. If the amplitude continues to shrink, which I don't know, and the number of cogs, you kind of get like it's one of these limits that is, maybe it's a good limit for the area of the shape. The perimeter probably is very singular. But I don't know. You know, like this classic thing that the limits of steps like this, if you take the steps smaller and smaller, you eventually get the line, but the derivative of the steps is always 0, that kind of thing, you know, it's kind of the best. You know, the cogs get smaller and smaller.
But you fix the area, you said.
Yeah, the area is fixed to 1, always. That's the main constraint.
And then when you break up the domain, if you look at like dynamics, let's say, you start in a point and you see, you throw the angle and see where you end. If you stay in the same system, I mean, in the allowed region,
Yeah.
is it in a disconnected part of the most typically, because they seem like very thin.
You mean like out here?
If you have it like,
Yeah,
if you start in one of those tribes and you pick the angle,
I mean, look, you
I
can,
guess that those that increase, that make the probability increase would be angles that make you end up in another stripe.
you can probably guess what D is, right? Like D, what is D? It's probably about this.
No, so it's like
So you have some probability if you're in certain parts of the stripe to go from
Yes.
part to certain part of the stripe, but actually if you're
but
like
it's
here,
very narrow range of angles there, and the other is.
yeah, there's some sort of balance, I suppose, between these two
Can you
situations.
think of this if you regard this with some dynamics where some period dynamics? I don't know, something that you change, maybe
I don't know.
that you jump from one.
Can you comment on the opposite problem, where you're given an arbitrary shape and you ask what's the optimal D?
Sorry. Oh, well that's, you just do this integral. I mean, you take, let's see, right? You perform this integral. Right? This gives you, for any omega, or you have the optimal D, sorry. I went too fast there. You want for a given shape, I don't know, I thought about it. Presumably it's easier because it's a one-dimensional optimization problem. So you can just compute, if you can use integral for arbitrary D, you compute it, and then you just do take the derivative of 0 and solve for D.
In ecology, there are fragmented landscapes where animals move around with a certain step size,
Oh, interesting.
so there could be a motivation there.
It could be nice, but I mean, it's a much simpler problem because, again, it's an optimization in one dimension, whereas this is an optimization in infinite dimensions. So, I mean, this you can do. You just, even numerically or analytically, you compute the integral as a function of D, and you include the maximum.
I think what maximizes V is D equals 0. Because in evaluation, but in ecology you have a good reason why.
It does, I mean,
that's not.
D equals 0 does maximize. As you can see, this red line is the probability. It goes, bigger D is bad for the probability. Anyway.
But then if you need food, you start with this. More questions? Okay, so let's think there again.
They can use emergency solution.
These are unexpected. With I think nothing that you